Okay. Hi, good after. Well, we are almost afternoon here. Welcome back to the workshop. So we are getting on to topic 4 on industrial digital infrastructure. So we'll be hearing from speakers, experts from the industrial landscape. So our first speaker will be Professor Maxime Lafrancois. He will talk about an overview of the World Wide Web semantic communities polarization, about how to encode quantities of value in RDF. Professor Maxime Lefrancois is a former student of the École Normale Supérieure d'Éducation, and he prepared and passed his agrégation examination in mechanics in 2008. He holds a master's degree from Grenoble in signal processing in 2009, and in informatics from the University of Grenoble in 2010. During his PhD work, he worked on knowledge representation and reasoning for the meaning text, linguistic theory. Between 2014 and 2017, he was a postdoctoral researcher at the École de Saint-Étienne. He was one of the co-editor of the SOSA SSN standards, and the leader of ETSI specialist task forces. Since 2017, he is an associate professor in the Connected Intelligence team at the École de Saint-Étienne in France. Our second speaker will be Thomas Engel. He will talk about the GEMIMEG 2 project, creating a digital infrastructure for Industry 4.0. Dr. Thomas Engel studied physics and mathematics at the Technical University of Darmstadt. He finished his PhD in 1997 on laser development and precision spectroscopy for the applications to determine the age of the universe and test the aspect of special relativity theory. So in addition to that, he studied medical physics in the Goethe University of Frankfurt. Then he changed to industry in different combined management position in R&D plus operation and innovation management. His field of work was at wavelength precision metrology and on lithography masks for the leading edge wafer production, on interoperative radiotherapy in medical technology, and also tactile and optical sensor systems and coordinate measuring machines for industrial metrology. So in 2014, he founded his own consultancy business for innovation and technology management. In 2015, he joined Siemens Technology as a principal key research scientist for optical technologies and perception. In that function, Thomas is chair of this GEMIMEG 2 project that he'll be presenting later, right? And our next speaker is, maybe speakers are Mark Huster and Michael Schwartz. They will talk about the digital framework consideration for measurement information infrastructure, MII. So Mark Huster holds a bachelor's degree in electrical engineering from and physics from Southern Methodist University, and a Master's of Science degree in electrical engineering from the Georgia Institute of Technology. He consults with 29 years of metrology experience He chairs the NCLSI Metrology Practices and MII and Automation Committee. And if you read the measure, you know that he writes the metrologies towards a measurement information infrastructure column and serve as the managing editor of the NCLSI Measure, the Journal of Measurement Science. Right. And Michael Schwartz completed his training in the Laurie Air Force Base in 1989 and was honorably discharged after 11 years serving the U.S. Army. He graduated from the University of Maryland with a degree in business management and a minor in computer science. After leaving the military, he spent the first 5 years as Intercal lead developer, writing automation calibration software before starting his own company. Since 2003, as the principal owner of Cal Lab Solution, he worked and developed the world's largest library of MetCal procedure, as well as design a whole new software platform called the metrology.net. So with that, we'll hope that you will again have a fruitful time listening to these 3 presentations from our expert from the industry. Thank you.
Hello everyone. So in this video, I will provide an overview of the W3C Semantic Web community polarization about how to encode quantitative values in RLEF. My name is Maxime Lefrançois. I'm Associate Professor at MIN Saint-Etienne, France. And some of these slides and the work behind it has been prepared together with my colleague, Antoine Zimmermann. So we are both participating in various community groups and working groups in the W3C, and also in the past. And at SC in a technical committee called Semantic Web. So the usual way and most common approach to encode physical quantities on the web of data is actually using an ontology of measures. And there are many of those out there. So here, quantity value would be encoded as an IRI and would be linked on one hand to the unit using a triple, and on the other hand to a value encoded using an XSD literal. We claim that it's quite complex to represent, process, query, compare quantity units encoded this way. So there is a very good survey that was proposed, published last year by Jan Martin-Cale and Cirko Schindler on this topic in the Semantic Web Journal. Our approach is to propose that actually, as one physical quantity is one value, and this is atomic, we should consider that one value will be encoded in one literal. And we propose a data type called CDT-UCUM, and one literal using this data type actually encodes together a pair of a number and a unit. So using CDT-UCUM, what we can do is talk about everything and all the quantity values that surround us. Like we can talk about Celsius, we can talk about Kelvin for the temperature. We can just use percent if we wish to, or use micrograms per cubic meter. So this is based on the unified code for units of measures, which is a code system intended to include all units of measures being contemporarily used in international science, engineering, and businesses. It's used by international organizations and standards. No ambiguity or almost none is possible between units. This standard proposes a clear semantics for units. And one of the main cons is that the terms of use of Ukum is quite problematic. This is the anatomy of CDT Ukum literal. So we have a lexical form, that is everything that is in red, and a data type IRI on the right, which is CDT Ukum. And as you can see on the bottom of this image here, CDT is actually a prefix that you can expand, and CDT Ukum is actually a full URI, right? On the left, we have minus 4.5. So this is encoded the same way as you would encode XSD decimals. Then optionally, we have an exponent, then a space, and then any string that would encode a valid unit, Ukum unit. So here we see that we have pi, a constant, that is divided by 2 and multiplied by radian, so a unitless unit of measure, and then kilo Kelvin at the exponent 4. In RDF 1.1, data types have the following anatomy. So first, they are denoted by one or more IRIs. Then they are, well, they have a lexical space. So this tells you what set of Unicode strings will be valid for this data type. They have a value space. So for CDT Ukum, that would be the set of quantity values that you can possibly imagine of. And then there is a lexical to value mapping, which maps a lexical space to exactly one value in the value space. A string in the lexical space to exactly one value in the value space. RDF 1.1 defines extension points. So RDF processors may recognize data type IRIs, and the set of data type IRIs that RDF processors may recognize is open. Once our RDF processor is designed to recognize our data type IRI, so it should be able to detect lexical forms that are valid or not valid for the data type. So this being said, ill-formed literals or valid literals. And it should also compare literals based on their value and not just based on the string that is used in the lexical form of the literal. Then we have SPARQL 1.1. So SPARQL 1.1 is the query language for the Semantic Web community, for the Semantic Web. And SPARQL 1.1 defines 4 extension points that are really useful for CDT Ukum, if it for the specification of CDT Ukum, and that we relied on. So the first is operator extensibility. So comparison between literals to order them or whatever is based on for numbers in SPARQL, it's based on XPath functions. And the specification SPARQL 1.1 says that we can very well extend what can be compared, with the less or equal sign, for example. Then we have XPath constructor functions. This is important to cast literals. So, for example, you would be able to cast literal that is, encoding 25 meter to some XSD decimal, for example, and you would obtain 25. Or you would also be able to cast, if you encode, data type URI for meters and data type URI for millimeters, you could cast the 25 meters and obtain the value in millimeters, for example. There is a third extension point for value testing. So we can define functions, for example, to check if 2 literals have a commensurable unit, or to extract the unit of a literal. And fourth extension point is for custom aggregates. For example, to extend the min, max, average aggregators to be able to do the same on quantity values and not just on numbers. So for CDT-OCUM, this is quite useful, and we actually implemented that. That's the next slide. So we can filter literals and filter them to get only those that are less or less than a certain length. For example, we can order them. We can add or subtract simply literals that way, and multiply and divide quantity values, or multiply a quantity value with a number, for example. So this has been implemented by us on in a fork of the Apache Gina, RDS, and SPARQL engine, and you can actually test it. So it's live on the web. So this is a screenshot of our playground where you can test and manipulate literals with the CDT-OCUM data type, and multiply them or divide them, or see what are the different units that you can use for acceleration or angles or areas or whatever. On the right, you see the results, and you see that we have actually defined also sub data types for sub value spaces and sub lexical spaces. So we have, for example, CDT length, where the unit needs to be a unit of measure that for length, etc., etc. So in a nutshell, CDT-OCUM is a unique data type to describe all physical quantities in literal. So we claim that it's very simple, intuitive to just write the number and then the unit, flexible, powerful, and it's also necessary, and the community needs such data type, because we have plenty of use cases where we need to encode quantity values and manipulate them as easily as possible. So now on the question, what the Semantic Web community do, or how do they encode quantity values in the web of data? Actually, there are various sub-communities in the Semantic Web community, and they have different approaches because there is no one common standard. So the way things are done in schema.org is very different from the way things are done in DBpedia. In schema.org, they have they use their own code for units. In DBpedia, they have data type URIs for meters, data type URI for millimeters, etc., etc. In the OBO community, they are converging apparently to the third approach below, where the unit is encoded inside the data type URI. You have the QUDT approach that corresponds to the first to the graph encoding approach. The linked building data community adopts OCUM. The Web of Things community is a bit waiting for what will come up. In this workshop, I would love to see the presentation by Simon Cox and Steve Ray. I didn't have the chance to do so yet, but I'm pretty sure that this is really interesting. So and brings lights also on other ways to do in other communities and in QDT, for example. What I will try to do here instead is summarize the polarized view of the community based on a very long thread that happened on the Semantic Web mailing list of the W3C last summer, and also an issue, very long issue with 60 comments already, number 129 on the SPARQL 1.2 community group GitHub repository. I will attempt to summarize the opinions of the following experts, so 24 experts from the Semantic Web community. Of course, this is only a partial view, and I chose to focus only on the aforementioned threads and issue. but this already gives us some general lines, general ideas. So we have some consensus. The community considers that a data type for quantity values, or many data types for quantity values, and support in SPARQL engines would be the way to go. Data type support in RDF and SPARQL engines can be a plus, but it should remain optional. And we agree that a standard for encoding quantity values is urgently needed. CDT-OCUM is appropriate use of RDF data typing and extension points of SPARQL. However, the OCUM terms of use are scaring out people. But as far as I know, hopefully they are going to be revised, and maybe hopefully they'll adopt something more in the lines of you know, well-known open source licenses. In the community, we still have divergences on whether the unit should be inside the lexical form, as we do in CDT-OCUM, or whether the unit would best be encoded in the data type IRI. And third and very important point, so we can listen to the community for requirements for a specification of data type IRI, a data type for encoding quantity units, quantity values, sorry. We would need operator extension, we would need custom functions to compare data type, to compare literals or to manipulate literals. We would need some casting conversions. We would need potentially to be able to have a canonical unit for every dimension, or define a unit ladder mechanism. For example, if you add some meters to some millimeters, what would be the unit in the output? We would need some kind potentially of web service where we can either send our literals so that and get the comparison or the conversion or you know, the addition or whatever, or potentially also a kind of web service where we can, from where we can download some script that would help us to manipulate literals with that data type. If I try now in the remaining 4 or so minutes to summarize the pros and cons of the 3 main approaches, this is what I would say. So about encoding quantity values in graph structures, the main issue is that we have like more triples, right? But we also need to retrieve relevant triples and reconstruct the quantity before being able to manipulate it and add quantities or whatever. We have to account for cases where we would have missing triples. However, this way to represent things using graphs will anyways be necessary for more complicated things. For example, when you want to encode measurements, if you want to model the fact that you have a measurement with that is 2.5 meters plus or minus 1%, for example, and you use a literal to encode this with a certain data type, measured data type here, with this data type, we wouldn't be able to define a proper semantics for that, or define you know, arithmetic operators or comparisons between measurements. If we use an infinite set of data type IRIs that encode units, so for sure we don't require to parse a compound literal. However, we need to parse IRIs. And furthermore, we need to compare, we need to parse potentially an infinite number of IRIs. So our SPARQL engines and our RDF processors will need to recognize or support potentially an infinite number number of IRIs. If we go for the approach, for the Okum approach, there are some characters that are not allowed in IRIs and in Turtle or SPARQL local names for prefixed IRIs. So the Okum atom characters are taken in the range of, ASCII values 33 to 126 minus a few ones, and some of them are actually forbidden to be used in IRIs, or some of them need to be escaped in IRI local names. Okum has this very nice feature of using defining annotations with curly braces. However, curly braces are characters that are forbidden inside IRIs. And third, the characters for operators like for multiplication and division would need to be escaped in IRI local names. So we would end up like below with, for example, Newton times meter here, where we need a backslash to escape the dot. And tons of IRIs would be equivalent. With our approach of CDT Okum, where the unit is encoded in the lexical form, so we need to parse the lexical form, right? But we claim it's more intuitive for users and engineers because you have just the value and then the unit. And it makes clear that this as a whole is one atom, so quantities are not numbers. So we don't want someone that just sees a number and then specific data type to just imagine that this is a number. It's a quantity, it's not a number. This avoids to have to parse an infinite number of IRIs, and less characters in Okum units need to be escaped in RDF literals. So I'm running out of time, so I just say that the three requirements that were raised by the community still apply here to CDT Okum. And so we really much look forward to maybe go further with this data type and see a community like making a standard out of it. What is important is that actually we don't want to make implementing the future version of SPARQL as burden. So we really believe that the specification of CDT Okum, for example, should be an auxiliary standard and defined by a potentially a different standard development organization, like is the case actually for GeoSPARQL that is developed by the OGC for encoding geospatial geometries. So this is the end of the presentation. Don't hesitate to send questions by email to us or ask the sources of our findings, for example. We'd be happy to answer any questions that you may have. Thank you very much.
Dear ladies and gentlemen, I'd like to welcome you to my talk on the GEMIMEG 2 project. The project is about creating a digital quality infrastructure for Industry 4.0, and I'm the project coordinator of the Industry Consortium. And as you can see on this slide here, the name is consisting of three different parts. As an acronym, the GEMIME for the digital twin, metrology, because we really focus on metrology aspects, and global, so that it can be applied internationally in a real global kind of application. Our aspiration is to create a safe and robustly calibrated metrological system for the digital transformation. To give you a brief overview, here's the project in a kind of nutshell. We started August last year. The funded budget is about 11 million euros. The total project budget is in the range of 18 million. The project duration is 36 months, and we do in total have 13 partners. 8 of them are out of industry, and you can see the different partners here. Then we also have the German National Metrology Institute included, the PTB, plus 1 research institution and 3 research groups from different universities. And the entire project is funded by the German Ministry for Economy Affairs and Energy, following a decision of the German Bundestag. What do we do? At the beginning, we had the observation that our world gets digitized everywhere. So we came up with a question, why not the calibration ecosystem too? And of course, the aspiration is to have a seamless integration from the National Metrology Institute down to the local applications. And how we consider the situation, we just have here a very brief view chart of a typical national quality infrastructure. So it really starts at the consumer and the general public, because they are really using the products produced by industry. Then we do have the different enterprises who should deliver the products. And in order to secure the quality, we do have on the top the national standards body or national standard bodies and the National Metrology Institute plus national accreditation bodies. They are interlinked because due to the accreditation and the standard bodies, the standard system of units, the digital SE is used. And this is then transferred by the different calibration processes, either from the National Metrology Institutes or from the accreditational bodies to the calibration laboratories or testing laboratories, inspection bodies or certification bodies. And in order to really provide reliable measures and artifacts, we do always have accompanying these measures or artifacts a digital calibration certificate. And this is then in the end handed over to the enterprises, either from the calibration laboratory or from the different other bodies. And in the end, it is used in the companies as a benefit to the customer to secure the product quality and, of course, the compatibility when different suppliers are in the supply chain. In fact, also it enhances safety and health, and it decreases environmental impact. That's a general aspiration, and I think most of you can or do have comparable structures in your own countries here. What was a typical production cycle? So where to bring in the concept of the GEMIMEG project? So just looking on the artifacts and a representation of a measure or a unit, we start with a calibration. When this is done, for the calibration, measurements are done and performed. Then the data which is gathered in the measurement gets analyzed and a report on the calibration is generated. Then the artifact plus the calibration report is handed over to the quality management in industry. From there, it's brought into production. And usually there's also a lot of optimization cycles in the industry just to improve profitability all the time in order to be really economic effective. And after a time, based on the ISO standards, there is time for recalibration. So the artifact needs to be returned into the calibration cycle and needs to be requalified. So the whole chain starts from the beginning again, and this needs to be seamless. And when looking on the production and the optimization, which is a core unit or core topic in the industry, that's where the money is earned, but that's also where Industry 4.0 and the digital twin is aiming at. So that's why we say here we can have a lot of contribution when the whole chain we are showing here is really digitized and also seamlessly using the data from the calibration in industry in order to make sure that the calibration results do not get sacrificed or disturbed in the transfer process. What is our research agenda according to it? So at first, of course, we are looking at robust digital calibration information to replace the paper-based system we are seeing right now. In order to make it digital, we of course need a future-oriented communication infrastructure on the one side. Plus, we do need a safe data orchestration on the other side, just as a, let's say, core or base environment. Then, of course, we have to take care about the sensors. So we need reliable multi-X sensor. Multi-X is just representing that it could be different units to measure, different modalities, and they could be combined in a sensor. So that's why we suggested this acronym of multi-X sensors. And on the other side, of course, not only the data measured is important, but also the quality level of the data and that it is accessible by the later user of the data. I will come to that on one of the next slides. And in order to show the feasibility of the entire project, we have planned a real bet or different real bets. In some, they are 5. We do have one in the competence center of wind power, then one for automotive, which is autonomous driving, then 2 in the pharma and process industry, and 1 on the Fab of the Future, which is directly aimed at Industry 4.0. Okay, so when looking at the base infrastructure, as already said, on the lower side here in the slide, we do have the test and calibration devices, the sensors. Then we come to a middle layer, which is the fog layer or the edge layer. And in the end, the result also ends in the cloud layer, where one or multiple clouds could be. The data is transferred there and can be used then by different users. So as said on the slide before, we do have on the one side here the secure orchestration of the data, and on the other side, of course, any conclusion and action, because in the end, we want to use this data for the production environment. And on the other side, of course, in order to meet also the cost requirements in the industry, we also have here the coexistence of high precision, high quality sensors and cheap sensors, and probably need to use intelligent methods in order to always validate the quality of the cheap sensor with respect to the high precision sensor in order to get the system costs down as much as reasonable. From a sensor's point of view, it looks the way like it is sketched here. So we start in the lower left corner with a physical sensor, and the physical sensor is used and probably built into a machine or a system. So we have to have a sensor to application calibration and the related information. Then we also do, of course, have the measurement values, so the sensor value qualification to correct for any sensor physics and also any kind of influence from the measuring process. And in the end, we also might have the sensor abstraction here, where we convert the measured sensor values to data plus some quality information on the data to make it a bit more abstract for the later utilization. And in order to make it transparent, there might also be some further blocks here on the semantic sensor information plus the traceable sensor calibration information. And all of this here, of this lower group, is brought together and just here for the sake of simplicity named sensor datum. Then the data can be cropped, or all the data can be used, or regions of interest in the data can be used. And then the relevant part of the data is forwarded to the data processing, and in the end, some output is created. This is the flowchart just from looking from persons who want to install and use sensors, what their primary interest is. To bring all of this together, we just have sketched here some GEMIMEG concept, where we start on the left-hand side here, just with a measurement and values domain. Then we come to the sensor and data aggregation domain. And in the right-hand side, we only have the data utilization, which means all the data is available and is utilized for the purpose it is intended for. And everything here, since we are in the modern IT infrastructure, is of course based on the safe data and asset orchestration plus the communication infrastructure in a fog architecture. So when looking on the left-hand side for the measurement domain, we do have the sensor itself, which is taking the data. And then we have the measured values, plus, as already mentioned, the quality of sensing information, which is coming out of here, these kind of measurement conditions, operation conditions, and environmental conditions of the sensor. And then the calibration data, which is incorporated there or generated. All this can be used in the digital calibration certificate plus accompanying information. And then this information, of course, gets forwarded here to this middle layer for the sensor and data aggregation. So when we do have the data from multiple sensors, which need to get fused in the sensor data fusion, have multimodalities and so on, the data is used. Plus each datum from each individual sensor is carrying also its quality of sensing information. And when we do have then the fused data, in the end, we do have an output here with the data and also feed through a quality of data information, which is generated from the quality of sensing information. so that we always have the dualism between the real data and some quality measures in order to help in the end the application or the data utilization in the digital twin, or when generating information out of the data, so that they can assess a trust level, how much the result gained from the data is trustworthy or not. During the course of time, just to see if there are any changes over time. Okay, that's the general process. Now let's come back to the digital calibration certificate, which you're seeing here. From the general process, as already mentioned in the first digital calibration certificate conference, the customer organization is requesting a calibration and inputting all the different data fields on the customer organization itself. It's selecting a calibration organization and specifies the kind of calibration requested. This is handed over then to the calibration service provider, and all these administrative data then are taken over and also supplemented, of course, by the real data of the measurement environment used. Then the measurement takes place like we had in the production cycle, which is now here in green. And then data gets derived here from the calibration process. So it's the qualification of the measurement. That's like it is today. And then a digital calibration certificate can be issued. And then also based on the digital information, the customer can have a real printout of the digital calibration certificate information when it is needed, and it can be generated anywhere because we have secured and encrypted or verified or signed data. And in addition to that, like I mentioned on the slide before, for the quality of sensing and quality of data, of course, we also added here the chance that quality of sensing information and determination or quality of data determination is also added in the process, which can be supplementary information in the framework of the digital calibration certificate. And then this information is also available in the production cycle in a trusted and verified manner, which is, of course, the goal of our project. What does it really mean in the practice? So the benefits for industry, I just used a very simple example just for a caliper gauge here. So when doing a measurement in general, we do have an intolerance region shown in green, and we have on the both sides the out of tolerance regions, and then we do have also the intermediate regions, which is the upper tolerance limit and the lower tolerance limit. That's how every single measurement can be described here. And just when taking about the caliper gauge, for example, we want to have precise and secure information about the metrology system, which can help to shrink the tolerance budget. This means that here in this chart, we are really having the orange trace from the calibration. So we really know for each individual measurement object what the specific individual tolerance is, and we do not need to rely on the much broader general ISO tolerance band specification, which for a caliper gauge is around 50 micron in many cases. So here we can really take advantage when we really know the real calibration data. And the advantage is because we know the uncertainty of the caliper gauge more precise, we can really shrink in this lower and upper tolerance limit, where the region is where it's not clear if the product is in tolerance or out of tolerance. And just like shown here in this sketch for the both sides, the tolerance band can be, or the tolerance limit uncertainty region can shrink significantly. And this in the end yields to a very good situation, because the intolerance band is increasing, which is the green range here in the middle. As you can see, it's increased, and this directly yields into higher yield and higher productivity of the production system. And therefore, the direct result is a return of invest, because you do not have to scrap as much products as before, and therefore you directly improve your cost structures. And when you do have a seamless process integration, it is key, because then you always can be sure that you are utilizing the real specific tolerance values in order to avoid any errors or to increase a very cumbersome work of really importing lots of data. So the seamless digital integration is key in order to really improve production without tightening specification. And I think that's a real good lever for industry to also take a little bit of effort for the digitization, because the return of invest might be much larger. Just to remind you, we are here those 13 project partners, which are gathered together in this GEMIMEG research project funded by the German Ministry of Economic Affairs and Energy. But that's not all. When we applied for the project, we had a long list of partners and supporters supporting us with a letter of interest. It's about 30 organizations, as you can see here. And we are really grateful that they supported us. So the next step from our project is that we will bring them or give them the chance to get or to become associated partners of our project, and therefore to get in direct discussions and to get an integral part of our projects. And now I already started the summary of the projects. The data in the digital quality infrastructure for Industry 4.0 really needs to be findable, accessible, interpretable, and reusable. So it needs to follow the FAIR principles. And in addition, of course, because we are talking about metrology, the information needs to be traceable as well. So, and that was our aspiration. The GEMIMEG 2 project is aiming for a standardized, secure, and traceable implementation from the sensor to cloud and to the application, of course. And in this respect, we do have this broad consortium and still want to integrate further partners and contributors, because they are highly appreciated when we want to have and want to create a system which can be standardized and really used in general afterwards. You have to integrate as many different kind of perspectives in the beginning to be on the safe side that what you are creating is open enough and it is versatile enough so that it can support everyone. And with this respect, if you are really interested, or if you're interested in the project, want to be part of it, want to become a partner of it as an associated partner, please feel free to reach out to me, or if you want to have more detailed info on the project, please check out for the website gemimeg.de or from the German Ministry of Economic Affairs. For the moment, the homepages are only in German, so if there is some other demand, please come back to me, and then we can talk about how to integrate you into our project. This all for the moment. I hope I could give you a little bit deeper insight into the project. Thank you for your attention, and yes, now we can go into a Q&A session later on. Thank you very much.
Okay, welcome everyone, and thank you for attending. Thank you also to BIPM for setting up this important workshop, and the session hosts and moderators. My name is Mark Custer, and today I'd like to talk to you about the measurement information infrastructure that NCSL has worked on for some time, and how it relates to the digital framework and digital SI vision of this workshop. So we'll talk a little bit about NCSL, the vision of the measurement information infrastructure, current status, and how it relates to the digital framework and the DSI. So as many of you know, NCSL was established in 1960 in the United States, partially in response to the interoperability issues that we are still discussing today in a different paradigm. It's a volunteer-driven organization. We have an annual conference. We publish quite a few standards and practice documents, as well as provide training tutorials and webinars. Also published the Metrologist magazine and the Measure journal, all of which you may find at the website shown. In 2015, the NCSLI reformulated the existing 141 Automation Committee to focus on the MII and chartered it to develop the data structures and other support for that MI and to facilitate related products such as software. We've published updates in Metrologist magazine and CalLab magazine, and you can find complete details on the project at this website. So what is an MII? What does that mean? Well, it stands for Measurement Information Infrastructure, and we defined it as follows. Basically, a set of standards and other support for locating, communicating, and sharing measurement information. And you see that it melds really well with the FAIR principles: findable, accessible, interoperable, and reproducible. So our vision centers around this diagram of the measurement information economy, in which measurement information producers send information to data consumers via these three information vehicles, namely the certificate, which everyone's familiar with, both test and calibration certificates, the measurement instrument specifications also, and accreditation scopes. Now, in each one of these measurement transfers, data transfers, which occur for every single measurement made in the world, we have blockages because a human is required to manually produce these documents in most cases, and in almost all cases, a human at the receiving end interprets those documents and transcribes them into their own IT systems. So the vision of the MII is to automate all these information exchanges so that they flow smoothly and we can reap the value from that. This slide captures just a few of the many automation possibilities that might result, up to including the capability for calibration labs to automatically generate calibration procedures and produce the data in response to a request based on the data contained in the various instruments, the standards, and the UUTs in their calibrations certificates and in their instrument specification documents, as well as the lab's accreditation scope. And these benefits flow all the way from conceiving of a process or product and identifying its requirements to finally producing and testing that process. So where do we stand? If we go back to our central diagram, we started out by identifying rough orders of magnitudes for the numbers of these documents and the numbers of these entities. And you see right away that the accreditation scope has the fewest number of concrete instances to try to meld into a single data model. So we started there. Now, we did develop high-level data models for all three documents because they all center around the same type of measurement, same type of data, namely measurement information. From there, we set up a testbed database that contains schemas for quantities and units and filled that database with test data. We developed an accreditation scope schema, a detailed schema for representing statements of accreditation in an XML format, and set up a repository that will take those XML documents, validate them against the schema, and allow users to search on them with a smart search interface. So not just a text interface, keyword search that we typically see on A/B sites today, but a smart search that uses the measured value and the desired uncertainty to find a desired CMC. So from that repository, we went to what we call Qualer Search, which collected 250,000 CMCs from the accreditation bodies in the United States into a single database and allowed a visual search on those parameters by measured value. Now, commercial organizations, including CalLab Solutions and Qualer, have provided support for this efforts, as well as a number of member volunteers. So this shows an example of Qualer Search, which you may find at this website. So we're searching here for a mid-range temperature capability, and all the labs with accredited capability at that particular point show up on the map. So you have hundreds of labs, for example, in this area, another 100 or so in this area. And you can drill down to the individual lab instances. If you click on those instances, it'll show you the accreditation scope from which the data came. And this is just a test demonstration project. So some of the accreditation scope data is outdated now. But if you look at what happens when we search for a higher temperature, you see that it narrows down the field of accredited labs significantly. So that's just one demonstration of the many powers that we might obtain from digitizing this data. Now, Fluke Corporation has been working on the instrument spec side of things in a project they call Qubit, which you'll find at this website. Gives you free access to all of the instrument specifications that they've accumulated to date, well over 200,000 now. They aim to capture the specifications for every measuring instrument on Earth, which they estimate in the range of 3 to 4 million. And if you go there, you can use that to automatically generate calibration data sheets or calibration schedules for a given instrument with your requirements. At Sandia National Labs, at the Primary Standards Lab, they have a testbed project going as well. This one deals with the calibration certificate. So in this project, they embed their normal PDF certificates that they issue to the customers with XML data. It has the digital measurement data along with the taxonomy tags to identify that. So the customer may use the certs as they usually do. They're human readable, but if they feed them to a data processing system, then they could extract the digital data with its identification tags and process it automatically. Now, in working on all these projects, it's quickly came to light that none of them will reach their full potential without a defined and standardized taxonomy, at a minimum a taxonomy of measurement processes and measurands. So we've worked on that for quite some time. In order to make all these information exchanges machine readable, unambiguous, standardized, and interoperable, it really requires a taxonomy to glue it all together. So this shows some of the work we've done along that line. We've drafted over 200 individual taxons now and put them on this website for community review and feedback. There's a single taxon defined for each measurand, for each unique measurand process. And that's what appears in the digital documents. The human readable documents may show various aliases for the single measurand, for example, for differing languages around the world or just simply for different terminology. We define each taxon by describing it as either a measurand or a source of the measurand, and we proceed from there from the general quantity kind down to the specific measured quantity. Each definition defines the required and optional input and influence quantities, and they look like this as an example. Here we have a test process for sourcing voltage, in particular alternating current voltage in a sine waveform. So you have a basic description, the required parameters, in this case voltage and frequency, and optional parameters such as the load impedance of the unit under test and perhaps its connection point if it has multiple connections. As a result of this process, you have a UT indicated voltage or perhaps its error relative to the reference standard produced along with its uncertainty. While developing this taxonomy, we also started an accreditation scope editor so that users may develop these accreditation scopes easily without knowing anything about XML. And while we await that completion, we continue to work on the taxonomy and a schema for holding the taxonomy. Once we have those two things developed enough, we will finalize version 1 of this XML schema for accreditation scopes and involve some partner calibration labs and accreditation bodies to review and refine that format. And we'll continue to work with partners worldwide on digital certificates and instrument specification documents. Down the road, we hope to present the SOA format to ILAC and perhaps BIPM and publish a document specification. This screenshot shows one screen of the accreditation editor. It's a freely available tool. Accreditation bodies may brand it with their logos, and if they desire. It has a built-in math calculation engine because the MII documents have capability for embedding measurement functions and equations of various sorts. So for example, with CMCs, one may define an arbitrary function by which to calculate the uncertainty so that searches for a particular value may automatically calculate the uncertainty and compare that to the requirement. So how does MI relate to this workshop's digital framework and DSI vision? If you look at the technical requirements we've identified for an MII, standardization rises to the top. So we'd like to use existing norms as much as practicable. And that requirement, as well as the others, relate very strongly to the requirements identified in related projects around the world, including interoperability, perhaps the feature requirement, making all this data machine readable without human intervention via the metadata. Completeness, very important. So if you think about today's practices, they stem from working with paper and pencil, and then word processors, PDFs, email, all these manual processes. If you consider the GOM's advice to err on the side of including too much data rather than too little, then that becomes a good paradigm by which to consider formats for these digital documents, namely to discard no data. So humans may have information overload if too much data appears on a document, but that doesn't apply to computers. So if I include all the relevant information in a digital document, that gives us many capabilities down the road. So for example, today we may discard the various correlation coefficients on measurands on a certificate, and we typically do not include all the upstream traceability data to the SI, typically only showing one link in the traceability chain. Also identity, so to identify all the reusable data elements within a given document for reuse. Extensibility, to make the document formats forward and backward compatible through various revisions, and of course security and revocation capabilities. If you look at the documents, they all center on measurement data, which in effect means quantity values with the metadata tags to identify them. So a standard DSI representation becomes crucial for all these documents. Also, we might think about where to host these standard taxonomies and references. So for example, defining quantities, units, accredited labs and such, and who might host those descriptions. Calculable equations are a central issue in these documents for digitization, whether to calculate the CMCs and statements of accreditation automatically, to automatically convert between the quantities a user may want to search on versus the quantity represented in an SOA or another document. The instrument models that instrument spec documents would contain that will parameterize at time of calibration in order to describe the instrument's behavior in practice and to correct measurements at any point in the instrument measurement space. So in view of that, we throw out here a few possible topics for discussion, such as the taxonomy, what its structure might look like and where it might be hosted. Perhaps to talk about a reusable quantity value structure, a base class, for example, from which to build further classes such as measurement results, influence quantities, etc., rather than a flat file format as we see in the current proposal. Maybe to conceive as this Celsius temperature, thermodynamic temperature conversion as a quantity conversion rather than a unit conversion. How do we preserve exact unit conversions, protect them from unnecessary rounding? What about arbitrary precision numerics for future use in case we want further precision in the future? And what about uncertainty distribution parameters? If you'd like to join us in our work, we typically host a meeting on Mondays at 2 p.m. U.S. Mountain Time at this website. And if you have any comments or feedback or questions, you may contact anyone listed here. And like I said before, find further information at this website address. So thank you very much for your attention.
Okay, thank you very much for the three very interesting talk from the industry. The first one from Professor Maxime Lefrançois is a very specific area of the semantic web where the semantic web community is using a lot of the units, description of the units for their work to manipulate and do computation. The other use case is in the case of an example of a Industry 4.0 application, and again it illustrates a very interesting digitalization scenario. And the last example is the MII work done by NCSI, and that may perhaps be a bit closer to the domain of the NMI. So the CAL labs are part of the typical national measurement systems, and so they have similarity in what the NMIs are doing, and they derive a lot of the so-called traceability from the NMI. So I think this is a very interesting three different use cases of digitalization and where the units of measures are expected to play some roles. So today we are very pleased to have three, well, I have three, but now I have two. Okay, we are very pleased to have three panelists, but I see only one now. Our technical specialist is offline. Just hold a moment. We have some technical difficulty here. Okay, Benjamin, is all the panelists live now? All right, great. Okay, sorry, we had a little bit of a technical difficulty, and you can see now we have all our panelists live on the workshop here. First, I will give the opportunity to our panelists to introduce themselves. So perhaps, Mark, you can start first.
Okay, thank you. My name is Mark Custer, and I chair the 141 committee at NCSL that works on the measurement information infrastructure and automation. And pleased to be here to answer any questions you may have.
Thank you. Michael?
Thanks. I'm Mike Schwartz. I run CalLab Magazine, CalLab Solutions, and I work with Mark Custer on the 141 committee.
Thank you. And Matthias?
Yes, my name is Matthias Lampe. I'm with Siemens Limited China, based in Beijing, working in a research group that is dealing mainly with industrial IoT technology. And I'm here today on behalf of Thomas Engel, who gave the presentation of the GEMIMEG project.
Yes. Yeah, thank you very much for agreeing to be on this panel. So we are very pleased that at least two of the speakers are here and representative. Unfortunately, because of the time difference, Professor Maxime Lefrancois is not able to be part of this panel. So I will have Victoria read us any question that if you have posted any question on the chat box at the moment.
Thanks, Tom. We have a couple of comments that have come through, but we've got a question now from Mark from Rod White. He says, great talk. I'm very interested in the Measurand definitions. How would you cope with Measurands defined by procedures? For example, ASTM defines several dozen incompatible methods for measuring kinematic viscosity.
Okay, yeah, great question. Currently, we're dealing with a taxonomy for quantities, so viscosity would fall under that, and it would have perhaps the subquantity, kinematic, and any other qualifiers that go with that. But then in terms of the various methods for doing that, that kind of falls into a different part of our schema that deals with different processes and measurement methods for realizing any given quantity. The taxons, it would have a different taxon insofar as the different methods required, the different input parameters, different influence or input quantities. Mike, you may want to add something to that.
Yeah, what we're doing is we're building the taxonomies. So the idea is you have this top layer that's your taxonomy or a taxon layer. Then below that, you have the technique layer, which is the implementation. And at the technique layer, you can expand the taxonomy definition and give it more details that are required for that specific measurement methodology.
Okay, thank you. So Victoria, you have another question?
We haven't got any more questions in the chat yet, so I encourage you to send them through. But one that comes off the top of my head for the panelists is you guys kind of sit on the other side of the fence to metrologists. So do you have any thoughts on how to better make the connection to the metrology community?
You mean between the CalLab level and the NMIs or through BIPM?
I guess between the NMIs and the kind of work that you guys are doing, you know, also in GEMIMEG, I guess more broadly across all the NMIs, both NCSLI and GEMIMEG, if you both have a perspective on that.
Matthias, did you want to?
So yeah, so I cannot completely understand Victoria, but I try to answer nevertheless. So what I've noticed in the presentations is that still in our globalized world, some of these activities are a little bit on national level, right? So I think one thing that certainly would make a lot of sense, and that can probably be pushed forward also mostly by individual people rather than by institutions, is to have more exchange also internationally to make sure that not everyone moves basically in the same direction, but in a totally different way. So I think this is an aspect that certainly also events like this help a little bit to at least increase the awareness of similar things going on independently in different countries or different regions. And that is something where I think certainly some improvement is possible there.
Yeah, I think this is a great venue for making those connections and publicizing all the work that's going on in the different areas. Because we make a fair effort to locate and stay aware of all the different efforts that are going on around the world, but this workshop actually has brought several new ones to light that we weren't aware of. So, and we try to work at the practical, kind of the production level calibration work, yet leave space in the MII definitions so that we can capture the technical aspects all the way up to the NMI level. So we're happy to see what's going on at all the different levels and around the world.
There's a lot of little details we've got to work out. So what I'm amazed at, and I'm still amazed at, is date definitions. Americans will do day, month, year, or month, day, year. Europeans will do day, month, year. So that has a problem when you put that data in a database and try to move it around. And even getting down to numbers. Where's the comma? Where's the decimal place? Okay, between European and Americans, you know, we can't come together on these little things. So it just makes these bigger things even harder to come together on.
And think about it, like I'm located in China, so think about the additional complexity that comes in if you want to also support the local specialties of entirely different cultures.
Yes.
Thank you. So perhaps I can add on to what Victoria have asked. So there are, like I mentioned earlier, there are two different use cases. One is an Industry 4.0 use case. The other one is closer to what typically we might be called part of the national measurement system, the CalLab business ecosystem, right? My question first to the Mark or Michael, from the CalLab perspective, you're developing a systems that work for the CalLabs in your membership. What do you want to see, or how do you propose to work with the other quality infrastructure body, like the NMIs or the BIPM, or even in your case ILAC? So what is needed from these international bodies?
Maybe partially awareness, I think, of some of these efforts that are going on. We would definitely like to involve ILAC in particular in the work we're doing now with the statement of accreditation, because that obviously plays right into their field, as well as some accreditation bodies that we'd like to work with to prove and refine the system for creating these digital accreditation statements and the various details that are going to be required for expressing the extremely varied set of CMCs, calibration and measurement capabilities.
Mm-hmm, mm-hmm. So if I remember correctly in your presentation, you mentioned that the architecture of the system that you have now doesn't have the traceability so-called definition or linkage all the way back to the NMI at the moment. Is that correct?
Yes, I guess there's two aspects to that. So there's the three documents: the instrument specs, the accreditation statements, and the Cal certificate. And really it's the digital calibration certificates that would see the most value from including a traceability chain all the way back to the SI. And since we began work on the SOA first, we haven't developed the data model in detail for the calibration certificate yet. But in the meantime, of course, everyone is interested in the DCC, which is a great step forward. So we'd like to work closely with those folks to try to get our ideas melded together into this digital certificate format.
Yeah, great. Yes. At the plenary on Monday, the CIPM and the BIPM has talked about making their KCDB database machine readable. So I hope that is also one linkage maybe from the SI to the Cal Labs. Okay.
Yes.
Matthias, do you have any view on how, in the example of the Industry 4.0 application, the NMI or the Cal Lab can play a role in making it work? Or do you need anything from these two other organizations?
Well, I think in the long run, of course, based on appropriate standardization, of course, you will need the related services to have calibration certificates and other digital documents accessible over an appropriate infrastructure. And here I think it will take some work on the one hand side to form the technical basis, to have all the definitions and standardizations in place, but also to gain experience with the related infrastructure and with the related processes in the industry to make use of this infrastructure.
Okay, thank you. So this is my last question before we conclude this session. So this is directed at either Mark or Michael. What is from NCLSI and your membership, what is the clear business case for you to actually digitize your ecosystem?
I think that's there's several ways to attack that's in the slide presentation. One of them is just finding a calibration lab that's near you that can do the work. Each of the calibration labs are going to have different specialties, and you may not know there's a lab down the street that has, good people in there, well-trained people that can do that work. So the Qualer search can help labs figure out not just, can the lab do it, but imagine taking, a unit under test with 100 data points and throwing it in a search engine. And it tells you what labs can do all 100 of your data points with the accuracy requirements you need. Now you can send the business off to them, and then comparing it back to the GEMIMEG with the DCR versus the DCC, you could actually have custom data points. So you can send them a DCR that has your data points in it and get back the data that you need in your calibration. So I think there's a lot of stuff that this is going to do to help the industry move forward. And to pick on the NMIs just a little bit, same thing there. Is a lot of NMIs have the problem that their customers are requiring specialized data points. Same thing there, that you can start talking, not cal my unit, calibrate my data points on my unit.
Okay, thank you very much. So unfortunately, we ran out of time. Sorry, Victoria.
No, I was just going to remind you we've only got 7 minutes till the next session. So
yeah, so we ran out of time. So let us thank our panelists here for answering some of our questions and the interesting discussion that we have here. So we will have, and at the same time, of course, thank you, Benjamin, for running the show for us, making it smooth. Thank you, Matthias, too, and Mark and Michael, and of course, Victoria for posing the questions to our panelists. So we'll end this discussion session here.